Hi everyone, we are glad to give this presentation, RangeDet, in defense of RangeView for LiDAR-based 3D object detection. This work was done by researchers from the Institution of Automation, Chinese Academy of Sciences, and TuSimple. In our work, we propose RangeDet, an anchor-free 3D object detector purely based on RangeView. We designed several components to fully exploit the characteristic of the RangeView. Combining these components, RangeDet obtain high performances in the large-scale Waymo open dataset. So, one might ask, what is the RangeView? This figure provides an intuitive illustration of RangeView generation. The RangeView is the native data of mechanical scanning LiDARs. For a LiDAR with m beams and n times measurement per scan, the returned values from one scan are organized as a matrix with shape of m rows and n columns, called a range image. Compared with other popular representations, the RangeView has special advantages in some aspects. Pillar-based and voxel-based representations introduce quantization errors. The voxel-based representation is also computationally expensive. The point-based representation has to deal with unstructured data, which is not efficient in practice. Compared with them, the RangeView is naturally compact and has no information loss. With these benefits, RangeView-based methods make a success in LiDAR-based semantic segmentation. On the contrary, it is not going well for the RangeView in the detection task. So we would like to ask, why are the results of RangeView-based method inferior to other representations? To figure it out, we discuss some properties of the RangeView. First of all, although looks like a 2D image, the range image is 2.5D data essentially. So the 2D convolution might be not effective enough in range images. And, scale variation occurs in range images, which is not well addressed in current RangeView-based detectors. This is the overall architecture of RangeDet, a typical single-stage anchor-free detector. This figure shows two of our components, meta-kernel and RCP. For meta-kernel, we have some intuitions. First, the 2D convolution operates on regular pixel coordinates is not effective to capture 3D structures encoded by Cartesian coordinates in range images. Second, the neighborhood in RV is not identical to the neighborhood in 3D space. Thus, we obtain dynamic kernel weight from local geometric structures, making the convolution more effective to recognize 3D structures in range images. There are 4 steps in the meta-kernel. First, sampling, which means meta-kernel samples features in n times n window as 2D convolution does. After that, meta-kernel calculates the relative Cartesian coordinates between each sampling location and the sampling center, and uses the relative coordinates generate a weight vector for each sampling location by an MLP. Then, for each sampling location, the meta-kernel calculates the element-wise product between its weight vector and feature. Finally, meta-kernel calculates the output feature of the sampling center by concatenating all the products and pass the concatenated result to a fully connected layer. One may feel like meta-kernel is similar to some point-based operator, DGCNN, continuous convolution, for example. Here we make a comparison between them. Meta-kernel is defined in 2D RangeView, while point-based operators are usually defined in 3D space. Locations in RangeView are permutation variant, so it is much better to use concatenation. Points in 3D space are permutation invariant, so point-based operators usually adopt pooling to aggregate features in all sampling locations. Another significant difference is meta-kernel is much more efficient than point-based operators because it convolves on regular 2D range images, so meta-kernel can be used in large-scale data in autonomous driving. Another challenge in RangeView is scale variation, and the problem is even more complicated than in RGB images. For example, a nearby passenger car may have a similar area with a faraway truck but their scan patterns are largely different. Some scan patterns like intensity, density mainly depend on the range. So we assign ground truths to each pyramid level by their range. This slide shows the ablations of our proposed components. From this table, we can see that these components significantly boost the performance of our baseline by around 20 AP. In this slide, we discuss the study of meta-kernel. First of all, Table A shows that relative Cartesian coordinates as input are much more useful than relative pixel coordinates. One thing worth to be noticed, concatenation as aggregation is very critical as Table B shows. Point-based operators in Table C all adopt pooling or summation as aggregation. Moreover, you can see meta-kernel is very powerful in small objects as Table D shows. As we can see, using range as ground truth assignment criterion is superior to other strategies. In the comparison with state-of-the-art, RangeDet outperforms all the previous range view-based methods, and is overall comparable with BEV-based two-stage detector. In contrast to the stereotype that RangeView is inferior in long-range detection, RangeDet outperforms most other compared methods in the long-range metric, especially in the pedestrian class. To finish with, we paste the visualization of the predictions of RangeDet and ground truth. Thanks for your listening.